Welcome to Study Loop.
So in this problem, we have a certain gas that is going through two distinct processes that are connected in time, but the first process is going to happen under constant pressure, and this is going to be an expansion from V0 to 2V0. This is, for example, here, this constant pressure, starting constant pressure, and we have 2 points. Point here and point here, and here will be a straight line that is parallel to the volume axis. Now from this point over 2V0, the gas will enter an adiabatic expansion, meaning that the pressure will drop and the volume will increase, but adiabatically. So from here to here, for example, the pressure will not drop much, but it will drop. It will be a curve, adiabatic curve. It goes something like this. So two processes. First process here, and the second process here. You can also say this is the point 1, the point 2, and the point 3. And this is for the part A of this problem, to sketch the pressure volume diagram. Now for the part B of the problem, we need to find the total work done. The total work done is equal to the addition of the first process, the work corresponding to the first process, which is going to be an isobaric process, so W1 plus, and next it is adiabatic process. And so the work will correspond to the work of an adiabatic process, WT. Here we should substitute the corresponding formulas. The work done in an isobaric process, in this case, will be equal to P0 times the final volume, 2V0 minus V0. And for the adiabatic process, from the textbook, we know that the formula for the work done is going to be CV over R times, and here is initial pressure times initial volume, V0, 2V0, minus, now we have P3, this is pressure corresponding to the third state, the third point of the PV diagram, and for V0, which is the final volume. So here we can do some further substitutions, knowing that for an adiabatic process, the pressure P3 over P initial is going to be equal to the relationship between the initial volume and the final volume in this ratio over gamma. So this implies that P3 equals P0 times, and we can obviously see that V0s will cancel out, but this is for the later part, 2V0 over 4V0 gamma. This can be substituted here. And when we do this, we obtain, since we are asked to find the overall expression for this case, WT equals P0, 2V0 minus V0 plus, and then we say over R, and then we have P0, 2V0, and then we have to substitute actually minus P0, and then 2V0 over 4V0 on gamma times 4V0. When we cancel out all of the V0s, and but when I say that, I mean all of them in the whole expression here. So from here to here, and then we arrange it so we place common multiplicators outside of the brackets. We obtain that the final expression will be P0 V0 1 plus CV over R, and then 2 minus 2 minus gamma. So this 2 minus gamma is obtained when we arrange this part here, and just the 2 is from these two right here, and then the P0 goes in front, and then this P0 goes in front as well, and of course here we have only one V0, and then that V0 goes out in the front, and then we obtain this whole expression here. So this is for the part B of the problem. Now for the part C of the problem, we need to find the relationship between T3, the final temperature, and T0, the starting temperatures. This can be done from the relationship between the temperature, the pressure, and the volume for the adiabatic process. So from the textbook, we know that T3 equals T0 for this processes V3 over V1 P3 over P1, and then the ratio P3 over P1 can be substituted with, because it equals V2 over V3 on gamma for the adiabatic process. Also, we should know that V1 equals V0, V2 equals 2V0, and V3 equals 4V0. These are the conditions. When we substitute them, we obtain that T3 equals T0, and then the ratio for V0 over V0 times 2V0 over 4V0 and on gamma. Clearly, this will cancel out, this will cancel out, this will cancel out, and this will cancel out. So this is equal to T0 and then 4, but 4 can be said is 2 on 2 on squared, and here we will have, and there is a reason why we do this, here we have 2, 4, this will be 1, this will be 2, here 1/2 on gamma. But remember that 1/2 of gamma is equal to 2 on minus gamma. This is from the exponential rules, so 1/2 gamma equals 2 on minus gamma. So this is T0, 2 on the 2 times 2 on minus gamma, and this equals to T0, 2 minus gamma. Similar was done in the previous part of the problem. Therefore, T3 equals T0, 2 on 2 minus gamma, and this is the final answer for the part C. And for the part D, we will straight use the equation 19.25 from the textbook for the heat exchange, and CV T1 minus T2, and substitute immediately for the number of moles from the ideal gas equation and obtain P0 V0 over R T0, and then here we have CV plus R. This is because this is the relationship for the heat capacities, and then for the temperatures we know this is 2T0 minus T0. So when this subtraction leaves us with 1 T0, that T0 will cancel out with this T0 here, so these two will cancel out. Then we have R CV plus R, and when we multiply that with 1 over R, we are left with CV over R plus 1. Therefore, the final answer is Q equals P0 V0, and then in brackets CV over R plus 1 after this algebraic transformation. And this is the final answer for the part D, and now the whole problem is solved. I hope you find this helpful, and I hope to see you in another lesson. Bye.